Our next section is to look at charged particles moving in a magnetic field. So we've already considered a wire with a current inside it, placed inside a magnetic field. So if the current here was going up through the wire, the intensity of the current, and the magnetic field was going into the board here, we've learned that the current's up in the thumb, and the magnetic field is shown by the fingers stretched out, and so this would be forced to our left here as a force. Okay, and you've got a formula for that, F equals B sine theta. So the angle is important as well. In this case, the angle is at 90 degrees. It's up and the field is that way. What we need to look at here is what's causing that force to occur. We know it's based on the current because if the current goes down to zero, there would be no force. So what is the current made up of? Well, in reality, you've got electrons in here that are actually drifting down in this direction, colliding with atoms as they go. And that's because you've got a negative terminal somewhere and a positive one, and so they're being forced downwards by the electric field inside the wire. So the electrons are going downwards. So the direction of positive current because of that would be the result of, I guess, imaginary positive charges going this way, or as effectively positive charges going in the opposite direction to the negative flow of electrons. So you've got positive charges moving up in this direction, like that. So what we can be sure about is they've got a velocity of some sort, because it's going to drift up in that direction, the effective positive current, or positive charge, and this is what's causing the force to occur. So the question becomes, do you need the wire to actually get these positives, or they could be a beam of protons, to experience a force? So if I just showed a proton beam up here, would they experience a magnetic force instead of a current doing it? The answer is yes. So if we now just consider one proton travelling the length of this wire here, the formula we're supposed to use to work it out for a wire would be F equals BIL sine theta. Now we want to apply one that would apply to a force for a charged particle of Q moving at a velocity v. Can we get a formula that involves these two quantities which are more useful or more usable for a proton? It's got a certain charge, it's got a certain velocity, and it's going to travel this distance here. So let's have a look at this. If that's the length of the wire we're talking about here, L, how can we bring this into it? Okay, by definition you've got current is equal to the quantity of charge over the time. It's the rate of charge flow, so don't forget that one. So we can substitute that into here. We need a formula for length though as well. So how would the length be related to the velocity of that proton coming through this length of wire? So you've got velocity of a proton going along a length of wire would be the displacement over the time. Okay? So the length it's going to travel is the displacement, L, this is the one, over T. So you've now got V is equal to L over T. So for L, I could use V times by T in here. L is equal to V times by T, divide by T, times by T. If you now replace these in here, you've got B, I would become Q over T. The length would become velocity times by time, and you've got your sine theta still. Okay? Now based on that, you've got a formula F equals BQV. I'm going to do it as QVB, and rearrange it a bit, sine theta. And that involves the quantities that, for the proton. Its velocity and its charge and the field it's sitting in. And that will give you the force on the proton. It's based on Q, V and V, the charge, quantity of charge, the velocity and the magnetic field strength. We'll be focusing on this here. Okay, F equals QVB, but it is the same sine theta factor. All right. Now there's a couple of key differences about what happens here. If you imagine a length of wire, then you would have protons of positive, or basically positive charge drifting up effectively that way, if you consider conventional current, in all sections. Which means that all the way along the wire, you'll have a force on those positive currents there, pushing it to the left. And so the whole conducting wire is pushed to the left. That will not happen in the case of a proton being sorted as a single beam. So if you fire a proton with positive charge here into a magnetic field that's into the board, it does not be bound by the wire boundaries there. So it's going to be free to move. So when this first comes into here, there's going to be a force to our left, because if you use the right-hand rule here, that would be the direction of positive current, this moving positive charge here. The field is in, it's going to be forced to our left. So there's your positive current there, that way. Okay? And that's at 90 degrees. As soon as this starts to happen then, this is now free to move because it's not bound by a wire, and it's going to curve. And it's going to start to follow like that. And in actual fact, it follows a circular path. It's going to be a circular path. And the reason for that is, the the force is always at 90 degrees to the velocity. It's always at 90 degrees to the velocity. So when it's at this position here, you've got a velocity going that way as a tangent, the force will be here at 90 degrees. And if the force is always at 90 degrees, it's going to basically follow a circular path with no change in the speed, just a change in the direction. So it's going to supply the centripetal acceleration you would need to go in a circle. Okay? You could derive a formula then for this. Because if the magnetic force is providing the force of centripetal acceleration, you can combine the formulas. So let's look at that. The magnetic force here is going to be providing the force of centripetal acceleration. And you can come up with a relationship about the radius of this circle then. Because magnetic force we've just shown is QVB. And you can ignore the sine theta because we're just doing it for 90 degree situations where the velocity is in the plane of the page and the field is into it. Now the force of centripetal acceleration will be MAC, which is equal to mv squared over r. So if you look at that then, you can cancel out the velocities on each side once, and you could rearrange for r up the top here and get r equals mv left over there and qb at the bottom. So that's the formula you could use to work out the radius of any circle for a moving charged particle in a magnetic field. It's often rearranged like this, by the way, rqb over m, because that'll actually tell you the velocity of a particle that's actually bending in a magnetic field if you can measure its radius. So there's the two common forms of it. So what we're saying here is that any charged particle that's moving in a magnetic field will experience a force just like a current does, because the charged particles are the ones that are responsible for the current. So the size of that force will be the charge, the quantity of charge, the velocity, and the magnetic field it's in, and there is an angle involved. So here you've got a proton moving to your right there, so that's going to be the direction of your positive current now for your thumb. The field here is into the board. We would expect this to be forced upwards then as it enters this field here. So it should follow a circular path as it enters, going like that. Now, it may only just do like a quarter of a circle and leave the field, or it might get a half a circle in. But along this path here, this region in here, it's going to be circular. All right? And we've worked out that there is a formula you can derive for the radius of that circular path based on those four quantities there. Okay? Now, this means if it's going faster then, if the charged particle is going faster, we would expect it to be a larger radius circle that it forms, because they're proportional. By the same token, if we were to increase the field here, and it would exert a bigger force on that charged particle, and it would curve it in a more tight circle. So R is proportional to the inverse of B, like that. So the inverse is proportional. A larger field strength would exert a larger force and cause this radius to go smaller, and it would be a tighter circle, coming in something like that. And it might come in like that and actually do a half circle and come back out again. All right? So that's a very useful formula there. Just bear in mind that if the velocity was zero then, that this charged particle will experience no force at all, which is different to an electrical field. If you put a charged particle in any electrical field, E, it always experiences the same force. Okay, just the same charge there. So this is different. You'll only get a force while it's moving, and it's got to be moving at a component 90 degrees to the field. If it was totally parallel to the field, going to the board that way, it would not experience a force at all either. So if you actually had a charged particle released at a certain speed within a magnetic field due to a nuclear reaction or something like that, it would actually follow a circular path here. And at all stages you would find that the force here is always at 90 degrees to the velocity. And that's what causes it to go into a circular path. Because it's always at 90 degrees, there is no change in the size of the velocity, there's only a change in the direction. So this force is providing the centripetal acceleration. Here the magnetic field is in. Because the Earth's got a magnetic field surrounding it, and that protects us from the solar winds, because charged particles can come in and obviously do some damage to us. So the magnetic field deflects all of those solar winds, but it can actually cause particles in the belt here to gain enough energy to start to move around. But the magnetic field lines will cause it to follow a circular path. Now it's actually spiraled there because it's not just got a component of the velocity at 90 degrees to the field, it's got a component parallel which causes it to travel down along the field. But the magnetic force causes it to go in a spiral, and as these field lines become tighter, the field line is getting stronger. So therefore, as I said before, the radius of the circle here will become smaller, and so they start to spiral inwards and get in a tighter and tighter circle. And they follow the field lines until they get towards the poles here, and this is where you get them sort of mostly being directed towards the magnetic north and south pole, which gives you this lovely australis borealis or a aurora borealis, where you get those southern lights or northern lights because of this effect. Now, what would happen if you shoot a beam of electrons into a magnetic field instead, where it's got a negative charge? So that's the way that the negative charge flow is going. Then conventional positive charge flow, which is your thumb, would be going in the opposite direction. If that's negative current flow, positive current flow will be that way, okay, in the opposite direction. So that's the way my thumb's going to go to indicate current. This field is into the board, so it's going to be pushed by the palm in that direction. So they will curve in that direction, the means of the field. Whereas positive charges would actually curve in the opposite direction. Okay? So just bear in mind that the negative charges will curve in the opposite direction to the positives there. Here you've got a tube here with a gas in it, an electron beam going around, collided with particles in the gas, causing it to glow in a purple colour in this case. And it's following that circular path because there must be a magnetic field here applied all the way across this tube here, if you like.